Do you ever have that feeling, you know, when you go to turn on a piece of test equipment or a tool and it won't turn on because the battery is dead? So you plug it into the charger, you let it charge up for 3 or 4 or 6 hours or whatever the charge time is on the device. You unplug it from the charger and you turn it on again and it goes dead after like 30 seconds. And the pack is shot. Now, depending on the pack, some of these packs for specialized pieces of equipment like 3M test equipment, these are bloody expensive. A pack like that could easily be $50 or $60 or more. And quite often, the problem is the whole pack's not bad. What happens is one cell goes bad. What happens with nickel cadmium and nickel metal hydride, and even lithium cells for that matter, is to get to the specified voltage. In this case it's 4.8 volts. What they've got is each one of these cells puts out 1.2 volts. So the cells are all connected in series. 4 times 1.2 is 4.8 output volts. The big problem with all these type of batteries is as the tool sits in your toolbox, not being used for weeks on end, and you're not giving it a refresh charge because everyone thinks the same. These things, batteries charge, I turn it on and it'll tell me when the battery needs to be recharged. The problem happens is nickel metal hydride and nickel cadmium batteries all suffer a slow decline of their charge through internal resistance. Think of it like this battery pack here. As the batteries discharge on their own, each cell has a slightly different internal resistance, and it will cause the cells to discharge at a different rate. And then what happens is you grab your favorite tool, whether it be a drill or a multimeter or some type of test equipment, you turn it on. And you've got one cell that's gone dead completely. And your other 3 cells will compensate for that weak cell by putting out a little extra current. And what happens is the power gets drawn through the battery in the reverse direction. That can be demonstrated. My meter's going to need to be fixed here, I think, because my display is starting to act up on here. But that can be demonstrated with this pack here. I'll show you here. So if I connect my meter across this battery, you'll see that the voltage is 6 volts. When one of the cells gets weak, current is drawn through that battery in the reverse direction. And that battery will start to take a charge in the reverse direction. And once that battery starts to take a charge in the reverse direction, your voltage will drop. Now I'm only getting 3.2 volts, which is actually less than 3 cells because these cells are 1.5 each. 3 cells should be 4.5. But the cell that's taken on a reverse charge is now actually being subtracted from that voltage. And the pack is shot. Send us another $60 for a new pack. But you can usually resurrect these things, and I'll show you how to do it. Now remember I said that these battery packs are 4 cells in series. So if we take off the shrink wrap, on the cells, that'll leave us with the 4 separate cells. And as you can see, these cells are just spot welded together. The reason that there's 4 wires on here is because there's a little temperature sensor which is used for charging to tell the charging circuit if the battery pack is overheating and what state of charge it's in. Now by removing the shrink wrap, I can actually test each individual cell. If I test the first cell, you'll see that this one measures up to 1.3 volts. If I go to the next cell over, this cell here, it's only coming up at 0.9. This second cell here has gone bad on this battery. We go to the third cell, 1.3 volts. You guys can't see that. Zoom the camera out a bit here. Third cell over, 1.3 volts. And the fourth cell, it's also only 1 volt. So we may have two bad cells in this pack that are not taking a charge. These two are holding a charge, but these two are not. And we go back to this other pack here and we'll measure the voltage on these ones here. And we'll see that this one here, 1.2 volts, 1.1 volts, 1.2 volts. You gotta remember this is under no load. 1.1 volts. So there's a good chance that these two cells are getting weak on this pack. These two cells are okay. What I can do is I can actually break these two packs apart and get the cells out of these that are good and replace the cells on the other. So what I'm going to do here is I'm just going to break the packs apart. I'm going to take out the cell that's bad, which is this one here. I'm just going to cut the tab off of it here so I can solder it onto another tab from another good cell. So we'll take that one off. This is the battery that when we measured the voltage on this one, it was down at like 1 volt, 0.9 volts. So this battery is toast. And we're just going to find the best one from this other pack, because this other pack also won't charge up due to a bad cell. So we'll look at the first battery here. 1.2, that looks to be a good one. 1.1, that's a little weaker. 1.2, 1.1. So I'll pick this one from the end here. 1.21. This looks to be the best. The best chances of it being a good cell. So we'll just cut the tab here, and again cut the tab on the end here. And then all we need to do is just connect the negative terminal to the positive terminal of this battery, and the positive terminal here to the negative jumper from the other battery. I'm just waiting for my soldering iron to warm up, and then we can attach. So here we go. The batteries are connected in series. So I've got my positive terminal to my negative terminal on my little tabs that I salvaged from the old pack, and we'll just butt them up together and solder the tabs together. Now that I've soldered the batteries together, if I put my meter on here and measure the voltage, we'll find that our voltage is now 4.89. It's a 4.8 volt pack. I can now place this back into the device that it's designed for and put it on charge, and the unit should charge up as we've replaced the one cell that had gone bad in this pack. So here's my pack. Now I've reinforced it with wires on both sides here, just to make sure that my connection is good between the cells. We're not going to have any breakdown after it goes back together. And then when I do my final voltage test here, 4.8 volts. So that's exactly what the pack is supposed to be. I'm just going to wrap this up in tape so I can put it back into the device for testing, and we'll put it on charge overnight. And by the morning, my test meter should be back up and running and ready to put back into service. And there you have it. My battery pack is once again all sealed up. The thermal detection diode is placed between the cells just where it was before. That's to detect the temperature of the battery as it's charging. And I fully expect once I get this back into service tomorrow that there will be no more problems. Thanks for watching.